everybody. Welcome back to Chem 121. Looking at the schedule coming up, it looks like... Ooh, just a second, hold on. Had to cough there. Looking at the schedule coming up, it looks like we are getting really close to the exam, which is actually next week on Friday. So there's going to be some changes to the quiz schedule next week. We're going to finish Chapter 4 today, most likely. And I will let you know what's going on with the quizzes at the end of this lecture when we assign quiz number 4, because they'll be due a little bit early, so I can release the answers early. But quiz number 3 is due tonight, so make sure that you get that in by the deadline. There is a 24-hour window after that, which you can still submit it. Lab worksheet number 2, which is not really difficult for enough for me to spend time talking about it, is due Thursday the 5th. Really, all you need to know about lab worksheet number 2 is that there are a series of videos in the documentation file, and you basically watch the videos and then answer the questions based on your knowledge of chemical and physical properties. So we're going to be reviewing stuff from Chapter 1, and that's really the whole point of the lab, is to give me descriptions of things that you are observing. So observational awareness and skills are very important in chemistry, as they are in most professions. Your ability to perceive important information from the world around you is a very, very useful skill to have. So we're going to help facilitate that growth by giving you that assignment. Normally what we would have you do is we would have you in the laboratory doing experiments, and then you would write down what you see is going on in as much detail as you can. Obviously, since this is all at home, you can't do these experiments at home, and you'll see why. Because one of the experiments makes like this coiling... It's called the Pharaoh's Serpent, and you'll get why you shouldn't do this one at home. And then the other one is literally manufacturing aluminum cans, and then there are other experiments too. We don't have that sort of setup because it would be prohibitively expensive and or toxic. So videos, unfortunately, are the best alternative that I have. So do feel free to ask me any questions about lab number 2. I can't tell you the answers, obviously, because I'm grading that. But I can guide you in the right direction, of course. Okay. Oop, it says we're finishing Chapter 3. Ha 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 ha. Hold on. That should say Chapter 4. Alright, there we go. So, as a warm-up, we left on this exercise, and I feel like it would be worth doing this as a class. I mean, well, you guys do it, and then I'll guide you through the answers afterward. So, let me number these real quick. What I want you to do is write the symbol that is represented by this statement. So find what atom you are looking for on the periodic table, and then apply the change that I have prescribed here. So loses 2 electrons, what do you write for that? Gains 2 electrons, what do you write for that? Do those things for those 5 ions that you will be forming. We'll go over the answers in about 3 minutes. You can type your results in the chat to the best of your ability. I know subscripts and superscripts aren't a thing you can do here, but do the best you can. All right, one more minute. We'll go over the answer. All right, the summary of this lesson is that when you add electrons, you get a negative charge. Because electrons are negative, right? If I add -1 to 0, I get -1. If I remove electrons, I get a positive result. Because when you subtract negative things, you get a positive number. 0 minus -1 is +1, right? So if I lose 2 electrons, it's like I'm subtracting -2 from 0. So I would get a result of +2. If I gain 2 electrons for sulfur here, I would have that as my answer. Hydrogen losing its electron would be this. Platinum losing 4 electrons would be this. And then chlorine gaining an electron would be that. So there you go. Again, the trick is to remember electrons are negative, and from there, it logically follows basic mathematics. I know I told everybody that we were not doing math for a little bit, but basic math is sort of always with us. So the expectation that we can add and subtract is really never going to go away, unfortunately. All right. There's the homework practice for the section that we finished on Tuesday. Let's carry on. What we're going to do now is we're going to try and make ions. Now, I've already shown you the octet rule, and we said that atoms wanted to attain a full octet, right? They wanted to have 8 valence electrons, or they wanted to ditch all of their valence electrons if they had a small number, so that the previous layer would be their octet. So hopefully that makes sense. Can you be more specific about what you mean by the tables? Do you mean these tables? I should have a table in here somewhere. Apparently I don't. That might have been an earlier chapter, actually. You'll have to be more specific. If you ask me on the Discord, I can look at it. If you do that right now, during the break, I'll go look and I can maybe answer your question. All right, so let's make some ions with the idea in mind that, hey, I want to achieve the octet rule. Now, the reason that atoms will follow the octet rule is because, as we said on Tuesday, they want to be stable. In other words, they want to be unreactive. Now, as far as, like, nature is concerned, what atoms are doing when they react is they are releasing energy so that they end up in a lower energy state. It's the sort of same principle by which an object on a table will fall to the ground, because objects on the ground are at lower energy. They're closer to the ground. Things fall towards the ground. Things don't fall upward. So, by the same principle, reactions go in a certain direction. And there is an eventual end point for a given reaction. And for our atoms, that is, they have achieved the octet rule. They have reached the end point of their reaction, and they are more stable. They are less likely to react. So, what our goal is going to be is figure out what the fastest way to get our atom to the octet rule is. Now, this statement here, they will try to match the number of electrons of the closest noble gas to them on the periodic table, will work almost all of the time. There are some exceptions to this rule. But remember, count your valence electrons and then get to an octet. Do this in the path that is the shortest, because you may have multiple choices here, and we'll talk about that too. So let's look at oxygen. I gotta get this on the screen, so give me just a second here. Let's see here if I could find it. Oh, it's already captured. So, boop, there we go. So there's our periodic table. There's P table. You should know where that is by now. So if I click on oxygen here, you'll see that O is in group 16. That means it has 6 valence electrons. So if I draw the Lewis symbol for oxygen, we would draw this. And then I would put 6 dots down. Remember, 1 per side. And I can have my 2 pairs and my 2 unpaireds on whatever side I want. I just need to have the correct number of paireds and unpaireds. Okay, so there's oxygen. I want an octet. What's the fastest way to get to an octet? Well, if I have 6 and I need 8, I would add 2 extra electrons. And so the ion that forms would be this one. So whenever you see oxygen, you'll either see it as O in its atomic state, which is 6 valence electrons, or its ionic state, which would be with 8 valence electrons. 8 valence electrons is 2 more than it normally has, so we give it a charge of 2 minus. All right. So what I want you to do is apply this idea to these ions. So I'm going to give you a bunch here. And the strategy, again, is draw the Lewis symbol with the appropriate number of dots based on where it is on the periodic table, and then get to an octet. Once you get to an octet, write out the charge that occurs based on what you did. So if you took away 2 electrons to get to an octet, give it a 2 plus charge. If you added 3 electrons, give it a 3 minus charge, and so on. So go ahead and do these. I'll number them for you. And you'll notice one of these you don't have to do anything to. And we'll talk about what you do with that in a second, but try and type that answer in anyway with the rest of them. All right, I'll check in with you in about 4 minutes. I'll see you in a bit. All right, one more minute. We'll go over the answers. All right, so I'm going to write down the number of valence electrons right here. So number of valence electrons. We're going to make a little column here. So, and I'm just going to go through and I'm going to write down all, well, I was going to write them down and then my tablet decided to glitch out. For what it's worth, that's not a tablet issue, that's a PowerPoint issue, because this doesn't happen in Photoshop to the same degree. All right, so hopefully I got those right. Otherwise, I need to actually look at a periodic table. All right, now remember, our goal is to get to an octet. So let's start with the easy ones first. So in order to get to an octet here, I need to add 3 electrons. So my phosphorus would look like this to start. So I have 5, and I'm going to add 3 more. And I'm gonna use these big circles. Let me make this one filled in here to show which ones I'm adding. And then, since I added 3 electrons, I would get that. Well, I wouldn't get that. That's boron. Oh, come on, PowerPoint. There we go. So that would be the ion that we get for that. And then down here for astatine, to get to 8, I have to give it an electron. So astatine would look like this. 1, 2, 3, 4, 5, 6, 7. And then I have 1 extra electron that I add there for that. All right, what about the ones where it would be a lot to add them? So I can't add 6 electrons. That's way too many, right? So in order to get to an octet, what I actually have to do is get to 0. Because remember, if I get to 0, that's like having an octet, right? The previous layer down becomes our octet. So barium here starts with 2 electrons. I would get rid of those. And there's my ion. Same thing for aluminum. We'll get rid of its 3 electrons here. Just cross them out. I should underline my answer there. There we go. Oh, look, I made a mistake already. Nobody caught it, though. So selenium doesn't have 2. I was writing its charge down. Ooh, that's on the internet forever, isn't it? All right, we're going to give this 2 electrons. So selenium starts like this. See, even Instructor West can't count to 8. No, I really can't. Counting is very difficult. There you go. Now, what do we do for this last one? It already has 8, right? So, what do I do? Well, the answer is you don't do anything to it at all. So for krypton, you're already just done. Krypton already looks like this, doesn't it? It's got 8 already around it. It already has an octet, so it's not going to react. Remember, it's a noble gas. Noble gases don't react, so they don't need to move electrons around. Now, if you only have one of a charge, since this question just came up in the chat, the convention is that we don't write the number 1 for the same reason that we don't say, like, if you have NH3 for ammonia. Where'd my cursor go? There it is. We don't write this, right? This 1 here, we don't write that. So 1s in chemistry are usually implied. So we would just do something like this, although there wouldn't be a space there. And then how do you find the keys for the quizzes? You should be able to find those in the assignments tab once you have clicked on your quiz attempt. All right, so there's the solutions for that. Now we know how to make ions. And remember, every time you have an element that follows the octet rule, you're going to form an ion in this way. What's the shortest path to get to the octet? We're going to be doing this a lot today. So just remember what we did on this slide, where we either removed electrons to get to 0 or we added electrons to get to 8. And that's going to be the ion that forms. After a while, you're not going to have to do this process anymore. You're just going to memorize that, oh, if I have aluminum, it's +3. Oh, if I have selenium, it's -2, and so on and so forth. So let's start doing that. Let's start putting these things together. So when we form a compound between elements, those elements will follow the octet rule. So here I have 2 ions. I have sodium plus and chlorine minus. And both of these follow the octet rule because sodium starts with 1 electron. We've ditched it. We've given it a plus charge, and then this is what we get. Chlorine has 7 valence electrons. We add another electron to give it a minus charge. And that's what we write for that too. Now, we've been treating these processes as individual things. I remove an electron. Okay, where does the electron go? Let's not talk about it. Well, now we're going to talk about it. Where does the electron come from when I add it to chlorine? I can't just create electrons, right? That would be violating the conservation of mass. We'd be creating matter. We can't do that. So we have to have a source for electrons to come from and a place for them where they go. And that is going to be from neutral elements. So for instance, if I did this reaction where I have sodium and chlorine, so regular old sodium, so this, and regular old chlorine, which does occur in pairs, and we'll talk about why that is in chapter... Oops, you know what? I put that on the wrong side. We'll talk about that in chapter 5. There's a specific reason I want to put it on the left side here. So, if I put these two things together, can you imagine a way that they would both work together so that both atoms have an octet? I'm going to let you think about this for just a minute. And then we'll draw out the answer, and then we'll see what actually happens when you do chemistry. Okay, hopefully you're looking at this and trying to move electrons around, because something has to give up electrons, and something has to take them, right? What if I did something like this? So I don't want this electron here. I need to get rid of it, right? What if I moved it right here? This right here, guess what? That's our chemical reaction. It turns out that chemical reactions are going to be involving electrons. And for the simplest reactions that we're going to study in this class, primarily speaking, we're going to be shuffling around electrons such that everything has an octet. And then once everything has an octet, we'll notice that cool things happen. Bonds form, we make new substances, etc. So let's show this actually in action here. So, oops, I hit the wrong button. I want to hit escape on my keyboard and then click on this. And so this should... No, I know my browser's up to date. Stop it. Sorry, I had to click on this like 13 times before it will actually load the video for some reason, because PowerPoint had an update, or I don't know. All right, so let me get Lonnie's lab here on the screen. I want this window here. I also have a cat, apparently. Hi. Oh, you're right there. Hello. I turned my head and the cat was right next to me. Okay. Kresnik, buddy, I have to teach. He wants me to pet him. All right. So I don't want audio for this because I'm going to talk over him. Okay. So this is Lonnie. Lonnie teaches at UC Berkeley, is my understanding. And what Lonnie's going to do is he's going to demonstrate the reaction of chlorine gas, which is Cl2, and sodium metal. Now, the first element that we're going to look at is chlorine. So if you look right here, you can kind of see that Lonnie's wearing a white lab coat. His sleeve isn't stained yellow because it got dunked in like something that had like a dye or whatever. The gas in this chamber is actually a pale yellow. This is chlorine gas. Chlorine gas is extremely dangerous. If you breathe this, you will basically die. This is one of the components of mustard gas, which you've probably heard of, used in World War I and II. Not good stuff. The reason that he is safe to work with this is because right here there's this ventilated grate, and all the air is being pulled into this around him. So this is basically a very fancy fan that draws air downward and then filters it through a bunch of filters before we eject it to the atmosphere. So Lonnie is quite safe here, provided that this tank doesn't spring a leak, which it doesn't because we have this valve on it connected to this hose. So Lonnie has charged the cylinder with an amount of chlorine gas that you can see. And then he will put the tank away. And the next thing he's going to get is the sodium metal, which is down here. Sodium is explosive with water, which we saw in the last chapter when we dropped it in water. We were talking about periodic table and stuff. What Lonnie's going to do is he's going to cut a piece of sodium and take it out of this bath, which is an oil bath. The oil keeps the water away from it because water and oil don't mix. He's then going to dump it in a solution of hexane and mineral oil and stuff like that. And this is purely just to wash off the oil. Now, once he's done this, he's going to take it out, and he's going to put it in this ladle, and he's going to heat the ladle up so that the sodium begins to melt. Now, because the sodium reacts with fire, with an orange flame, you're going to see this. So this yellow that's showing up here at first was the oil and the hexane that was burning off. But this bright orange that comes out is indicative of sodium metal being ignited. And once you see that, you know that it's hot enough for the reaction to start. So this color right here is sodium metal in fire. It is now hot enough that we can start the reaction. And so what he's going to do is he's going to put this right into this cylinder. And because we've heated this up, the electrons inside the sodium are excited. They're able to move to other atoms that they come into contact with because they're heated. Now, if we didn't heat this, it would just go really, really, really slowly. We're speeding it up so that the reaction will go more quickly. And so here's the reaction for the formation of table salt. And so what you're seeing here is electrons being passed from sodium metal to chlorine gas. And in doing that, we release energy. That energy is in the form of heat and light. You can see the light. It's hard to see the heat, but you'll see the heat in just a second. Now, the gas that's being formed, there is a little hole in here because you have to get the ladle in here. You can see that it's getting sucked into the vent. That gas is actually gaseous table salt that is being formed, sodium chloride. This cylinder is now filled with table salt. And when you take out the ladle, you can see that the ladle is red hot. That's how hot the reaction got. So he's going to set that down to cool. And you can actually see at the bottom here that table salt is starting to crystallize into a solid. And it's going to slowly sink down over time. And then what he's going to show here, and it's hard to see because let me do this and then move my cursor. Down at the bottom there, in the little watch glass is a sample of table salt that was prepared earlier using this method. And believe it or not, this is the same table salt that you eat with your meals. And Lonnie's going to demonstrate this by doing a lab safety violation, which is eating in the lab. So never eat your chemical reactions, although Lonnie's a professional, so this one's okay. So interestingly, what we have turned something into is, so we have turned a metal that is explosive with water and a gas that is extremely hazardous to human health. And by allowing them to react together, we've created something that is both inert, chemically, and delicious. So, chemical reactions are fun and interesting and have useful results depending on the reaction that you do. So, again, this is the reaction that we did. I've added this 2 here so that I have enough sodiums to react with my chlorines here. And the process that we just did, formally this is called an electron transfer. And visually, what that looks like is this. Here's what we drew on the previous page, and we said, hey, I can get everyone to have an octet if I did this to it. I'm going to just take this electron and I'm just going to fill it in the space right here. And then this is our result. Everything has an octet, so the reaction is complete. And then what happens? Well, I have opposite charges. What do opposite charges do? They attract to each other. So the process that we just did was we transferred electrons, and then the result that we get creates opposite charges that attract to each other, and that attraction is our ionic bond. So we are creating bonds by moving electrons. All right. So again, once you make a cation and an anion, they're oppositely charged, and so they come together through our ionic bond. So that's going to be our goal here in Chapter 4, is we're going to, 1, satisfy the octet rule to form an ion, 2, do the same thing to the other ion, and then 3, attract the 2 ions that are now oppositely charged together. So I have a bunch of these that I want you to decipher how the electrons move around so that you get the product. So let's do another example real quick before I turn you loose on these. Ooh, that's not what I wanted. I don't want this bigger. I want this wider. There we go. So let's look at this first one here, and let's do this. We'll move this over. I can't just hold the button down, apparently. There we go. All right. So let's look at this first one here. So I got potassium. That's not the pen tool. There we go. Potassium is in group 1 and has 1 valence electron. So there it is. I've got bromine here. Bromine is in group 17 and has 7 valence electrons. All right. Can I move my electrons such that I get an octet everywhere? And the answer is, well, I have 1 empty space and 1 electron to put there. So I would do that. And then what would my ions look like? Well, I'd have K. I lost an electron here, so this would be plus. I have Br. Here's the 7 electrons I had before. One of them didn't show up when I touched the tablet there. There we go. Here's the electron that I moved. It has a minus charge now. And then I'm going to just write out the ions that I had. So I have K plus, Br minus. The ions attract to each other, and the compound that I get is KBr. All right, I'm going to do another one for you. I'm going to do magnesium chloride here. So we'll scroll that one off the screen here. Because you're going to notice that an interesting thing comes up with this one. So magnesium is in group 2. It has 2 valence electrons. Chlorine's in group 17. It has 7 valence electrons. And so, just like we did before, we'll just move this one over. But where does this one go? And the answer is, well, I ran out of space on this chlorine to add electrons. So what I have to do is, I got to put this electron somewhere, right? I'm going to stick it on another chlorine. Because if I found one atom of chlorine, surely I can find another one, right? I can't get it to switch colors. There we go. So if you need another atom to provide space to put electrons onto, just grab another one. It's got to be one of the ones listed, though. So I can't just grab like a fluorine here. I have to grab either a magnesium or a chlorine to make this reaction finish. And what you're going to do is you're going to pass electrons around until everybody has an octet. So magnesium here now has an octet because I've gotten rid of both of its electrons, right? Chlorine now has an octet as well. In fact, both of them do. So let's write both of them here. Oops, I didn't do my little arrow there. So these are the ions that I have. I have Cl minus, Cl minus. And so what I do now is I just put these together in my formula. I have a magnesium, and I have 2 chlorine, so I would write this. And this is the formula of the ionic compound that I make. So that's our goal. Get everything to have an octet, and then put the ions that you have made together. You have to use all the ions, and you have to make enough ions so that you can move all the electrons so that everything has an octet. Some of these will require you to move multiple electrons to an individual atom. Others may require you have to keep grabbing extra atoms so that you can make the ionic compound. So that aluminum and oxygen one at the end there is going to be particularly obnoxious because you're going to need multiple ions of each type. Now, when you make the ionic compound, the charges are canceled out, right? So this positive 2 is canceled out by these negatives. So we don't put the charges in the ionic compound. So I think that answers both questions that just popped up here. So when you write out your ionic compound, the charges have attracted to each other and neutralize. If they didn't neutralize, they would attract other ions, right? So like if I had positive or negative left over, other things would be attracted to it. And then the formula would change. Now, we're simplifying this when I say that. Remember that ions form in an ionic lattice, so you're going to have a giant like array of these extending in all directions that makes those cubes that we saw in Chapter 3. But for our purposes, this is the simple formula that you can copy and paste to make that. How do we have Cl2? So you can take as many ions as you need to fill this in. Assume that all of the ions listed for each reaction are like a bank. So if you only need 1, you take 1. But if you need like 4 or something, you could take 4. Elizabeth, I'm not sure what you mean by the symbols don't matter. Can you be more specific? So what I want you to do, I'm going to leave this on the board as like a little guide here. I want you to do the Lewis structure in this manner for all the other ones that we just did. Or all the other ones that we haven't done. So we did KBr. And we just did MgCl2. So I want you to do calcium plus oxygen, sodium plus nitrogen, and aluminum plus oxygen. So I want you to try those. Draw out the Lewis symbol, move the electrons around until everything has an octet, and then write the formula based on what you got. And then type the formula into the chat here. I'll go back and number these. So we already did number... Oops, that's not the pen. So we did number 1. So do number 2, 4, and 5. And yes, we bring in the extra chlorine because we need a place to put the extra electron for magnesium. Chlorine can accept 1 electron, but magnesium had 2, so I had to bring in a second chlorine. Sometimes you need extra atoms. You're going to see in some of these that you do need extra atoms for some of them. All right, I'm going to check back in with you in about 5 minutes, and we'll go over the answers at that time. So see you in a bit. Oh, I just looked at the clock. So we are ready for a break. So what I'm going to do is I'm going to let you work on these through the break for the next few minutes and then go grab some more water. Go pet a cat. Do I have a cat over here? Yeah, I do. I'm going to go pet a cat. I'm going to put the break timer up here. We'll turn the music back on. And in 10 minutes, we'll go over the answers once we are done. Happy to answer any questions during the break, so just let me know, okay? I will see you in just a bit. Alright, we're back over here now. Let me wind this down. Hope everybody had a good break. I was about to go get water, and my cat jumped in my lap. So, Maya came to visit during the break. But I did get my water just in time. So, let's go over these problems now. So, we'll go back over here. I think I'm out of space, aren't I? Yeah, let's do this. And we'll, oops, ooh, that's not what I wanted. There we go. Yeah, cat is always more important than water, at least from the perspective of the cat, right? All right, so let's look at calcium and oxygen here. So how many valence electrons does calcium have? It has 2. And then how many does oxygen have? It has 6. And again, where are we getting these valence numbers from? We're getting them from the ones digit in the group that these elements are in. So calcium is in group 2, 2 valence electrons. Calcium's in group 16, 6 valence electrons. All right, is there a way that I can shove these around so that everything has an octet? Well, if I move one here, and I move this one here, then I have an octet on calcium and an octet on oxygen. So that would look like this. So I gave away 2 electrons for calcium. I added 2 electrons to oxygen. Everything has an octet, so we'll put them together. I have a calcium, I have an oxygen. Here are my ions. So, for a second, I almost wrote this. Because she just meowed at me. But that's... Sorry. You had to be here, I guess. I just heard I heard a cat meow in the background. I almost wrote cat. All right, so there's our compound. Now, as a check for this, what you'll notice is that these charges should always completely balance out. So all the positives added together and all the negatives should add together to the same number. So that's a check to make sure that you did this correctly. So check. Oops, I don't know what happened there. That's supposed to be a colon, but it didn't work. So double check that when you're doing this, that when you write all your ions out that you've created by following the octet rule, that your charges balance out, because they always will if you've done it correctly. All right, so let's do the next one. Let's do sodium and nitrogen. I need a little more space for this, but we'll just do that. So there we go. There's my sodium and my nitrogen. I'm going to move the 1 electron from sodium over to right there. And I need more electrons to go on nitrogen. It does not have an octet yet, so I need to have another sodium come into play. And it can go right there. And then I need still another sodium, because I only have 7 electrons here, so I need a third one here. And so this one will go over here. All right, now everything has an octet. So what we'll do is we'll write out what we have. So I've got oops. Oh, Photoshop, you're terrible. I really need to look into like a different program. So there's what we have made. Do all the charges balance out? I have +1, +2, +3. I have -3, so they do balance out. There's our ionic compound. All right, and then the last one, we have aluminum and oxygen, so I need a lot of space for this one, so I'm going to just scroll this all the way down. So this one is super obnoxious. So we know aluminum has 3 valence electrons. It's in group 13. Oxygen has 6 valence electrons because it's in group 16. And each oxygen can only take 2. So I can do this one, and I can do this one. But now I have no more space for this last one, right? I got to put it somewhere, so I need another oxygen. So there's my oxygen. We're going to take this electron and stick it over here. But now I need another electron. I don't have enough electrons to satisfy this oxygen's octet, so I need another aluminum. So we'll do that. And we'll put an electron here. So now this oxygen, we'll just put a little check mark next to the ones that are octet. But now I have 2 electrons that are left over, and I need to put those somewhere too. So I need another oxygen. And you just keep doing this until everything has all of the electrons it needs for an octet, or has removed all of its electrons to get to its 0, which again is the octet. So by doing that, this aluminum is good, this oxygen is good. We've made a mess of electrons. This looks like a terrible football diagram. We've made 2 aluminum with 3+ charges. I've made a bunch of oxygens. And they all have octets. And I'm going to be just super lazy here, and I'm just going to do this. Copy. Paste. Paste. Oh, I should move this first. Ooh, that's not what I want to do. Paste. There we go. Oh, and the window moved, because of course it did, right? There we go. I ran out of space! No! That's the worst thing that could happen. Okay, well, we're gonna have to go this way. Alright. Do the charges balance? Let's check. Positive 3 and positive 3 is positive 6, right? Negative 2, negative 4, negative 6. Wow, I don't know what happened to my plus over there. That was supposed to be a plus. That was definitely Photoshop. There we go. So they do balance out. So my ionic compound is valid. So there you go. All right. So this is what's happening at the atomic level when we're doing ionic compound reactions. Is the electrons are just shimmying about, moving to places where everybody has an octet, and then the resulting charges come together. All right, any questions, let me know. Because now that we've done this, we're going to work on the operation, or on the assumption that you can perform these actions behind the scenes. So if it helps you to draw out all of your stuff like this, like we just did, then absolutely do that. But at some point, you're going to get to the point where you just know these charges, and you're going to be like, okay, I know aluminum is +3, and I know oxygen's -2. So I don't have to draw the pictures anymore. And that's totally fine. What we're going to do from this point forward is we're going to just use the ions that we form, because we know aluminum makes +3. We know oxygen makes -2. And we're going to work from there. So let's do that. All right. So using our check that all of the ions should add to 0, once we've got all the positives and all the negatives there, we can write the formula for any ionic compound at all. We don't even need to draw the Lewis structures anymore. The Lewis structures are there to help us understand what's going on behind the scenes. So let's do this for some examples. Let's do potassium and sulfur. So you're looking at potassium. I know what ion potassium forms. It's this one, right? I know what ion sulfur forms. It's this one. And if you aren't sure of that, you can draw the Lewis structures, remember? We can say, okay, I'm going to get rid of this one. Now it has an octet. For sulfur, it has 6 valence electrons. I can add 2. So what we're going to do is we're going to just do all of this behind the scenes now. So I'm going to assume that you know how to do that. And it's okay if you're like, oh, wait, I have to still draw it out. Totally fine. You could just draw it out. In fact, I would encourage you to. And the more you do this, eventually you get to the point where it's like, okay, yeah, I don't need to draw it out anymore. But once we get to this point, we can say, okay, do my charges balance out? I have +1 and -2. My charges don't balance out. So this is not the compound that forms. I don't just put 1K and 1S together. I need another one, right? Now they balance out. So the formula that I would make would be K2S. So now we can do this without drawing the pictures. We can do it a little faster. If you prefer drawing out the pictures, that's fine. Draw out the pictures. The pictures are there to help you. All right. So using that idea, what I want you to try and do is for this compound, I want you to first predict its charges without drawing the pictures if you can. If you need to draw the pictures, go ahead and do it. And then I want you to write the formula. Now, I'll give you a hint. I've put these backwards. And the reason that I did this is because we've sort of implicitly been doing this already, but it's because I've been putting the positive ones first. So the positive ion is first in the formula. So when you write out the charges for these two things, don't just stick them in the order that I give them to you. The positive one always goes first. All right. I'm going to leave you to figure out the formula for this. It should only take you about 2 minutes or so. And we'll go over the answer in just a second. All right, let's go over the answer here. So what ions do each of these form? So selenium is in group 16. So the ion that it would form would be that. Barium's in group 2. There's the ion it forms. And again, you could draw the pictures if you need to. 2, the charges balance. Yeah, they totally do. And so this would be the formula we get. And everybody got it. Very good. All right. We've already done this one. I don't know why that's an example, because we've already done it. All right, but what I want you to do is I want you to do the same thing that we did before, but this time try and do it without the pictures, because you could do it a little faster. Write out the ions that each of these would form. So what ion will calcium be? What ion will chlorine be? And then put them together and balance out the charges. So I'll give you 5 minutes to do that, and then we'll go over them together in just a little bit. One more minute, we'll go over the answers. All right, let's go over here. And then I'll just do this. All right, so let's do the first one. So what ions will calcium and chlorine form? So calcium will form this one. Chlorine will form this one. Do my charges balance? I have +2 and -1, so I need more negatives here. So now they balance. And so the formula I get would be CaCl2. All right. Let's do magnesium. What ion does magnesium form? It forms this one. How about oxygen? Forms this one. I don't know what Photoshop is doing now. I need to reboot the computer, apparently. There we go. Those ions balance out. There's our formula. Next, I have sodium and phosphorus. Do my charges balance out? Oh, I only have +1 here and 3-, so I need more positives, right? So I need 3 of these. There we go. That balances out. And we can take a nap. Or an Na3P nap? I don't know. And then we have beef down here. This is absolutely not beef. Do not eat. So there's beryllium and then fluorine. I need more negatives to balance out my +2, so we'll just do this. Those balance, so we can write the formula. Remember, the formula is just how many you have. Just write it down. I have a beryllium and a 2 fluorine, so we'll write that. And then finally, for aluminum and sulfur down here, we know aluminum makes a +3 charge. Sulfur makes a -2 charge. So I need more of these. And now I need more of these. And now I need more of that. And I just keep going back and forth until I've balanced out the charges. So now I have +6 over here. Now I have -6 over here. There you go. All right, we have formed ionic compounds. So now you don't need the pictures to do it. So we can do this for any ions as long as we know the charge. We're going to use this in the next section, which is going to be to name these things. So the last thing we're going to do in this chapter is we're going to name ionic compounds. Oh, let me put the homework practice on the screen there. There you go. And then we're done with chapter 4. So we're going to finish chapter 4 today. All right, let's name stuff. Oh, real quick. Remember that ionic compounds look like this. So the formula that you are solving for in all of these is going to be the simplest formula that you can circle and then paste in a crystalline lattice. So ionic compounds are not molecules, like we said earlier. They are lattices, and the unit that repeats is called the formula unit. This is where formula comes from. So when I ask you for the chemical formula of your ionic compound, you're giving me the formula unit. So, all right. We've already kind of talked about that earlier, so we're going to just keep going. All right. For naming compounds, we're going to follow a set of rules. And the rules are deceptively simple. The first thing we need to do, though, is determine whether our compound is ionic. If it's not ionic, we cannot use these rules. We'll have to use a different set of rules, which we'll talk about in Chapter 5. So let's define some terms here that are going to help us identify whether we can name this using these rules or not. So the first label we're going to give is the binary compound. A binary compound has 2 elements. Now, specifically 2 types. There can be more than one of a given element, but there are 2 present. So here's my sodium, here's my chlorine, those are 2. Carbon and oxygen, those are 2. Phosphorus and oxygen, those are 2. Notice that the numbers don't matter. I could have 74 oxygens and 38 phosphoruses, and it's still binary, because I only have phosphorus and oxygen. But if I had 3 elements in there, it would not be binary. Now, an ionic compound, you've probably noticed this already. Ionic compounds have metals and nonmetals in them. The metals are the ones that give up their electrons, because they're on the left side of the periodic table. They're closer to being at 0 for the octet. Nonmetals are on the right side of the periodic table. They're closer to 8. So the metals give their electrons to the non-metals. This is what we've been doing all along. You've probably already noticed this, that there's always a metal in there and there's always a non-metal. And that we've never tried to do something with like chlorine and oxygen, or bromine and carbon, or anything like that. We're going to see what happens when we try to do something like that in Chapter 5. So the first check for naming is going to be, is it ionic? Can I use the ionic names in the first place? So here's our first example. Is this an ionic compound? And you want to check, is there a metal? Yeah, potassium is a metal. It's on the left side of the periodic table. Is there a non-metal? Yeah, bromine is on the right side of the periodic table. So yes. Yes, it is. All right. So I have a bunch of these. And because this is trivial and I only have about 20 minutes to go, I'm going to just highlight all the metals. So this is a metal. This is a metal. This is a metal. So if a metal is present with a nonmetal, these are ionic. These other ones down here are not ionic. And because they all contain 2 elements, we would say, okay, they're all binary. So I have binary ionic compounds, and then the other 2 are what are known as binary covalent compounds. We'll talk about covalent compounds in Chapter 5. Now, to name stuff, you can't just recite the letters. So, as much as it's convenient to say NABR, we need to give these systematic names so that we don't accidentally confuse things when passing information to other people. So, In order to be clear about naming these compounds, we're going to establish a set of rules, and the rules look deceptively simple. You're going to name the metal, then you're going to add a space, and then you're going to name the nonmetal, but you're going to append the suffix "ide" to the end. Now, very, very, very important. I'm going to warn you of this now because the quiz is going to get people on this. All right. When we are naming the metal and the nonmetal, do not use capital letters. Elements are not proper nouns, even the ones named after people. For example, oxygen is not capitalized. Neither is curium, which is named after Marie Curie, one of the most important physicists to do work in radioactivity. Without her research and her work, we would know nothing about radioactivity. Even though that element is named after her, and if you wrote Marie Curie, you would capitalize her name, we do not capitalize curium because we do not capitalize elements. Okay? If you do this in Canvas, it will mark your answers wrong. And if you tell me, hey, I got the answers right, but I capitalized the words, can I get credit? My answer to you will be, remember that slide where I said don't capitalize elements? This is that part. And I can't give you credit for it. So be exceptionally careful. The symbols are capitalized. So if I was to write out curium, I don't actually know the symbol for curium, actually, now that I think about it. Where is curium? Is it CR? Oh, it's CM. Okay. So here's curium. Oops. There we go. Don't capitalize it, okay? Be very careful. All right. So when you type in all of your names for these things, you're going to type all lowercase letters. Now, there is one exception to this, and it is not the element names. It's going to show up on this slide right here. So naming metals is easy if the elements are in these groups. So group 1, group 2, or the element you're looking at is aluminum. And the reason for this is because these elements have fixed charges. In other words, they follow the Octet Rule. And so identifying their charge is redundant. Saying sodium with a +1 on it is kind of silly because in all ionic compounds, sodium will always be +1. Because we've just done that, right? We spent the whole period today talking about what is the ion that sodium forms. Oh, it's +1. What ion does oxygen form? Oh, it's always -2, and so on and so forth. Now, you'll notice that there is a giant swath of elements that we have not been using. Things like iron and titanium and molybdenum and osmium. All the stuff in the center of the periodic table, right? Can those elements are metals, they're transition metals, can they be used in ionic compounds? And the answer is yes. Yes, they can. We just haven't been using them for examples yet, but they do exist. The issue with transition metals is that those charges that they form do not conform to an octet rule or any sort of rule that's easily predictable. In fact, it's further confused by the fact that those elements can have what are known as variable charges. So for instance, if I wanted to name something with both iron in it and oxygen, we know oxygen is always going to be this ion. But there are multiple different irons out there. There's this one, there's this one, there's this one. And if I were to say iron oxide, which one would it be? Well, I need to differentiate between these three. And the way that we do that is by using the charge. So if you are using an element that is not in groups 1, 2, or aluminum, like all the ones that we've used today so far, we've only been using groups 1 and 2 in aluminum. Those grouped elements that we just said, they all follow the octet rule. Everything else, however, does not. And because those still exist, we need to differentiate them. And here's what we do. If you have any other metal that doesn't conform to the octet rule, you have to include the charge as a Roman numeral. The Roman numerals are capitalized. These are the only capital letters that you will input into Canvas, is Roman numerals. Now, to be very specific, I'm talking about naming here. When you write formulas like this, you will still capitalize the letters in the formulas. So we've done this before. But with naming specifically, you do not use capital letters other than these Roman numerals. And the Roman numerals are only used if we are not referring to the elements that are in groups 1 or 2 or aluminum. Remember that. Now, what Roman numeral do you use? You use the charge on the metal. Now, just in case you don't know the Roman numerals 1 through 10, we can write them down on a slide. So let's do that real quick. So let me just do this real quick. So it's on the screen so we know what's going on here. All right, so on the left, we'll do the Arabic numbering. The Arabic numbering scheme is what we use, 1 through 10. And on the right, we'll do the Roman numbering. So we've got 1 through 10. And of course, I ran out of space, because why wouldn't I? All right, here we go. So in Roman numerals, 1 is just I, 2 is I, 3 is I, 4 is IV, 5 is V, and you can already see how stupid this is, right? This is how the Roman Empire fell. Their numbering system didn't hold up to the test of time. 6 is VI, 7 is VII, 8 is VIII, 9 is IX, and then 10 is X. There are really only 3 places that we use Roman numerals. One is the Super Bowl, or Superb Owl, if you prefer. The second place is Final Fantasy games. I think we're up to 16 now. 16 is in development. I have played all the 15 Final Fantasy games. They're all quite good. Except for Final Fantasy 13, which was terrible. Which is a shame, because I really liked the world it was in, but the game was just garbo. And then the last place that we use Roman numerals is naming ionic compounds. So, all right, so there's the Roman numerals. We're going to use those. And remember that the Roman numeral indicates the charge on the ion for the metal that we're looking at. You're never going to use a Roman numeral for a non-metal, only for the metal. All right. So the next thing we're going to do is we're going to name the non-metal. The non-metal is just whatever element is off the periodic table, but you're going to tack the letters "ide" on it after you've replaced some of the letters in the element's name. And you've probably already heard these names before. So you've heard of oxygen and also oxide, right? And so we're going to replace element names with what is called stems. So the stems are in your textbook. They're in table 4.2. But I'm going to write them down on this slide here. So let me scroll this down. Oh, I got to go back over here. And so we're going to write down all of the ide names. So we've got, so we'll start over here. So we've got fluoride. We've got chloride, bromide, iodide. Then we've got oxide. And Photoshop is really chugging, and it's really annoying me here. Sulfide. We've got nitride. And phosphide. Those are the major ones. So there's also, so like selenide is less common, but it does exist. I don't think we have to worry about arsenide, but there you go. So those are all the ides. And you can see that the stems are all the first parts of these elements. So nitrogen is nitra, phosphorus is phosp, oxygen is ox, and so on and so forth. So these are all listed in table 4.2. So have that reference handy when you are using it to name stuff. Remember that the ide form is used for ions only. And so I have an example here. That chlorine, without the negative charge, is just named how it is. But this minus right here means that we have to write ide for its name. All right, so now that we've seen all that, let's start naming stuff. So you're going to name the metal, and then name the nonmetal with ide. So I'm going to put this on the screen, and we're going to give it a name. So name the metal, name the nonmetal with ide. What is the name of this substance? Type it in the chat. All right, what element is K? This is potassium. And then what is Br? This is bromine, but I'm going to add ide to it instead. And there's the name, potassium bromide. Now, you'll notice here that it is capitalized my P, and the reason for that is because it has automatically capitalized it as the start of a sentence. So I'm going to just overtype them. Oops, I don't want to hit the eraser tool because it'll erase what I just did. So when you are following proper grammar rules and you start the sentence with a capital letter, that's okay, but Canvas is not expecting you to do that. You are not typing sentences into Canvas. You are just typing the names. All right, what would I call this? Type its name into the chat. All right, let's go over the answer here. Oops, I need the pen selected. So Na is sodium. O is oxygen as an ion at sodium oxide. There's your name. Now notice that we have not said anything about numbers. So whether there are numbers of elements or not, you just ignore these. So you don't say disodium. That's the next section. So be careful. Don't put number prefixes in there. Just follow the rules that we have done. All right, more examples here. What happens when I start using transition metals? Well, I need to indicate the charge in some way. So here I have cobalt, and I have a 2+ charge on it. You can't solve for or you can solve for this in some cases, but you can't just know which ion I am giving you if the element is a transition metal. So if I give you these two ions, you would first follow the same rules that you would for forming ionic compound formulas. And I would say, okay, I need to balance out the charges. And then I need to write the formula. So there's the formula. The formula, you can work backwards from the formula to get to this part, right? So if I give you the formula, you have to undo this process and say, okay, well, I have 2 chlorine and they're each -1, so my cobalt must be +2. And once you've done that, you can now name the compound. So what is this? Well, it's got cobalt in it, and it has a charge of +2, so I'm going to write 2 in Roman numerals. And then the Cl is chloride. Notice that there's no space between... Wow, I don't know what my pen just did there. There's no space... Oh my goodness. No space between the element name, or the metal, I should say, not the element name. Between the metal and the parentheses. So be careful, because Canvas will mark that wrong too if you add an extra space there. All right, there's your name. All right, one more. I'm going to give you this formula. And what I want you to do is, in the chat, type in the formula and the name. And then I believe we're out of time, so... So to answer your question there, so you already have the charge, you have to solve for it. So I've given you the charge because I've given you the ions. In some cases, I might give you the formula, which you would have to then break into the ions so you could give it a name. So since you already have the charges here, you don't have to solve for it. But when we come back on Tuesday, we're going to do some examples where I give you the formula, and you're going to have to split it into ions so that you know what to name. All right, let's go over the answer here. So first, let's write the formula. So I have a +2 and a -2, so those balance out. So the formula would be MnO. And then we know that Mn2 is manganese 2, and then O is oxide. So there would be our name. I've already written the name there, so we'll just do that. All right. So that is all the time that we have today, unfortunately. So here are the examples that I want you to do. There's actually 2 slides of these. So what I want you to do is over the weekend, try to do these examples. So this first page has no transition metals. And then the second page does. And then we have a little bit more on polyatomic ions because it's more or less the same rules. But for the most part, we have gone over everything that is necessary for the Chapter 4 quiz. So here's what's going to happen. So I'm going to post the Chapter 4 quiz later tonight when I have time. Because I had to go get set up for the next class at 2:30 now. So I won't have much time to do that this moment. But I'm going to put the quiz for Chapter 4 online. Now I'm going to set the due date to Wednesday. Or sorry, I have to set it to Tuesday. So that it closes Wednesday, which means that when we finish this up on Tuesday, you're going to have to finish the quiz either that night or on Wednesday night. And the reason for that is because I want the quiz to be open on Thursday so that you can look at it before the exam on Friday, because there is an exam on Friday and it will have all of this stuff on there. It will also have Chapter 5 stuff, which we still have to do. So we're going to be coming back to this. We're going to finish up Chapter 4 in the first 20 minutes or so. We're going to start with these examples. I'll just go through them. We'll talk about polyatomic ionic compounds. We'll do those examples, and then we'll jump into Chapter 5 and keep working from there. Chapter 5 also has its own quiz, but when we get to Chapter 5, I will tell you what I'm going to do about its quiz, because it will be due after the exam, but there are still questions about Chapter 5 on the exam, and I would like you to see the answers. So Chapter 5's quiz will be treated differently. All right. So all of that will be forthcoming later tonight. I do want to thank everybody for coming out to the lecture. Make sure that you ask me any questions. I see that there are questions in the Discord. I'm going to try and answer those real quick before I start my next class. But if you have further questions, please let me know. Either now or Friday or over the weekend or whatever. Happy to help. So let me get this going, and then there we go. Have a wonderful weekend. Make sure that you get quiz number 3 in tonight. Start working on lab worksheet number 2. It'll be due next week. And we'll see you on Tuesday. Take care.